Hello, it is Thursday night, recording for Friday's lecture. For this set of notes, you're going to need your reference table, so take a minute and pull that out if you actually have to pull it out. We're going to use table I a lot, and you will also need a calculator. Okay, so just a couple housekeeping things. The quarter ends a week from today. Next week we'll be wrapping up this unit and doing like an end of unit assessment that I'll grade for accuracy, and then basically that's it. And then we'll probably start unit 14. Haven't heard about going back to school on April 14th, but my guess is probably not. Anyhow, please open up to page 9 in your packet and let's get started. Okay, so today we're going to talk about enthalpy. All right, so enthalpy is the total heat gained or lost in a chemical reaction. Remember, RXN stands for reaction. Okay, so you have two types of reactions, endothermic and exothermic. Endo, heat is entering, so heat is absorbed, meaning that it is a reactant. In an exothermic reaction, heat is released, meaning it is a product. So just remember that reactants come before products. So literally you're just looking at the placement in an equation. So draw a line through the arrow. Heat is on the left, meaning it's a reactant. Heat is a reactant, means it is endothermic. Okay, so pause here and finish the next three. The number written in 3 and 4 is the heat. So when you see 3351, it's the same as saying heat, just giving it a value rather than a word. Okay, so go ahead and do that. And when you unpause, we'll finish this up. Okay, heat's on the right, exo. Heat term on the right, exo, because it's a product. Heat is leaving. Heat is entering, so that is endo. Okay, flip to the next page. This is where you're going to need your reference table. Okay, so in an exothermic and endothermic reaction, you're going to have a different type of delta H. So delta H is enthalpy, also called heat of reaction. Those three terms are interchangeable. There we go. Okay, so in an exothermic reaction, delta H is negative. In an endothermic reaction, delta H is positive. So that positive just means heat's being added, the negative just means heat is being released. Okay, so go to table I, and what I want you guys to do is find this equation. CH4 plus 2O2 yields CO2 plus 2H2O. So on table I, it is the very first equation. So take a minute and find it, and then write down its delta H. delta H is negative 890.4. So because it is negative, it is XO. So you also need to know how it's written in the equation. So it says rewrite the equation with the heat value on the appropriate side. So CH4 plus 2O2 yields CO2 plus 2H2O. So the only thing that's a little bit strange about exothermic reactions is that instead of writing like minus 890, the minus literally just means it's being released. So you would write plus 890.4 kilojoules. So when heat is in a product side, you do not include the negative even though it's exothermic, okay? It's just saying this amount of heat was released. Okay, so then it says, rewrite the last four equations from table I with the heat value on the appropriate side. Okay, so pause the video here and do that, and then when you come back, the answers will be there for you. Okay, so for the first one, it has a positive delta H, meaning that it's endothermic. So I'm going to add the heat value right here before the arrow. And then we have NH4 positive and NO3 negative. The water value here just means that NH4 NO3 is being dissolved in water. All right, for the next one, also positive, delta H, endo. So that's going to be NaCl plus 3.88 yields Na positive plus Cl minus H2O right here. Okay, and then next one, it's negative 48.83, which is exo. So this time heat is going to be released. So LiBr, H2O, Li plus, Br minus, plus 48.83 kilojoules. I should be writing kilojoules, but I don't really have a lot of space, so I'm not. And then the next part, negative 55.8 exothermic. Also as a product, so H plus plus OH minus yields H2O plus 55.8. Releasing heat makes things more stable, so it's good to have a release of heat in terms of stability. Okay. Okay, so the next part, we're shifting gears and we're talking about enthalpy of solutions. And this part is a little confusing because it's basically the opposite of what we've been talking about in terms of endo and exothermic. It's like kind of a different way of thinking about it. Okay, so the first law of thermodynamics says that there's a conservation of energy. Meaning energy is not created or destroyed. So the universe is composed of a system, which is like where a reaction occurs, plus the surroundings. So this is totally different than a phase change where we talk about like things heating up and cooling down being endo or exo. So I just want to preface that it's going to sound different because it is different. Okay, so when dissolving NaOH in water, the temperature of the water goes up. Okay, temperature goes up. So I'm dissolving NaOH in water. So if the temperature goes up, what is happening with heat? Well, the heat is being released into the water. So the system is releasing heat. The surroundings are picking up the heat. So this is an exothermic reaction. Heat is flowing from the system to the surroundings. it will feel warm to the touch, and the equation will look something like this. NaOH in water will split into its ions, Na plus, OH minus, and also releasing heat. Okay, for the next one, when dissolving NH4NO3 in water, the temperature of the water decreases. Temperature goes down. It's not a very good color for this. Okay, so this time I have something in water and it makes the temperature go down. So this salt is taking away heat from the water. The heat is going into the salt. So this is an endothermic reaction. So the system is endothermic. It's gaining heat. So heat is going from the surroundings, the water, to the system. It's going to feel cold to the touch. And the equation is NH4NO3 plus heat in H2O will separate into NH4 positive and NO3 minus. So this is like the reaction that occurs in a cold pack. So it feels cold because it's taking heat from your hand or your, your shoulder or whatever to create the reaction. And so it's taking heat away, so it's feeling cold to your skin. Okay, so we're not going to be able to do the activity, obviously, on the next page because we're not in the lab. But so I'm just going to skip it. But basically, it's just kind of like what we just talked about with the solutions. So we're going to skip page 11. If you want to do this later on your own, I can give you the data of what it would feel like. In this one, the beaker would feel cold. So that means it's endo, positive delta H. In this one, temperature would go up. So it feels hot, exo, negative delta H. This one is also cold, endo, positive delta H. So if you want to just practice those, this page on your own, you can. It's basically like what we just did on the previous page. All right, so moving along. I finally figured out the sweet spot for clicking over. Okay, so this is going to be our last page for today, page 12, and then you're going to have homework on page 13 and 14. It'll be due Monday at midnight, and then I will post the answers to it Tuesday morning since it's due Monday at midnight. Okay. All right, so stoichiometry with heat is basically like any other stoichiometry problem. It's just unit conversions. So when delta H is written as kilojoules per mole of reaction, it really means per mole of each of the species in the balanced equation. So this negative 92.38 kilojoules per mole reaction is when you have 1 NH2, 3 H2s, or 2 NH3s. So problems of this type are usually given to you in an unbalanced proportion, and basically you're just going to use this delta H as a conversion factor. Okay, so solve. It says using the example problem above, calculate the heat that will be produced if 3 moles of N2 reacted with excess water. You can just ignore anytime it says excess. All right, so I would start by 3 moles of N2, and I'm just going to cancel out the unit, mole N2, and I'm going to heat, so I want to get to kilojoules since that's what they've given me, heat in. So now I look up at my balanced equation right here, and I'm going to put a 1 because that's the coefficient for N2. I'm ignoring all the rest because they don't matter. Keep the negative sign as it just tells us that it's an exothermic reaction. So you get negative 277.14 kilojoules. Okay, in the next one, calculate the heat that will be produced if 2.5 moles of H2 react with excess water. So ignore the excess water. So you have 2.5 moles of H2. Set up the unit, so mole H2 on the bottom, going to kilojoules on top. So this number here comes from the coefficient right there. All right, so I'm gonna have a 3 here, and I'm gonna have negative 92.38. All right, so take a minute and calculate that out. I don't have that written down. Okay, so in my calculator, I would do 2.5 times negative 92.38 divided by 3, and I got negative 76.98. Oops, sorry, I looked away. Kilojoules, negative 76.98 kilojoules. Okay, so pause this video, practice the 2 at the bottom, and then I'll come back and show you the answers, and then that's it for today. Oops. Okay, so hopefully you tried those on your own. So let's just go through these. So in letter A, is the reaction endothermic or exothermic? So they gave you a positive delta H, so that means it is endothermic. Endothermics are written with heat on the left-hand side of the equation. So I would write CaCO3 plus 178 kilojoules, or you could just write plus heat, yields CaO plus CO2. How many kilojoules of heat energy would be absorbed if 3 moles of CaCO3 were to decompose? So 3 mole CaCO3, these are just like the ones we did in the example. There's 1 CaCO3 for every 178 kilojoules of heat. So you're just multiplying that times 3, and you should get 534 kilojoules. So this is like the 2 example problems we just did. Okay, on the next one, this is the heat. So since the heat is before the arrow, it is entering. It is endothermic. And then delta H is positive. How many kilojoules of heat would be absorbed if 16 moles of KClO3 were to decompose? So looking at KClO3, there's 2 of them, 2 KClO3, and I'm just going to write the heat off the top, 156 kilojoules. So 16 times 156 divided by 2, 1248 kilojoules. And then the next one, how many kilojoules of heat are absorbed if 1 mole of KCl react? This is kind of more typical number you would see. So they're telling you if you only have 1 versus 2, how much heat would you have? It's basically just going to be half of the heat that's given, so 78 kilojoules. And they remain positive because they are endothermic. One thing I did forget to tell you about, if you look at table I at the very bottom, let's say you forget what's positive, what's negative, it tells you the delta H values are based on molar quantities, blah, blah, blah. A minus sign indicates an exothermic reaction. So if you can't remember, table I is the place to look. And basically that's it. Okay, so once again, your homework is going to be on the next page, 2 pages, 13 and 14. You can take a picture of your work, and then I'll do the explanation Tuesday. So expect an end of unit assessment sometime next week. Alrighty, guys, I will see you later.